Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to be working with improper integrals. Okay, so thus far all of the integrals that you've worked on, especially through Calculus 1, have been proper. So what makes an improper integral? An improper integral is a definite integral that is not defined at least one value on the interval from a to b closed. There are two types of improper integrals. An integral that has an infinite bound. So if I were to write an integral and say I want you to find the integral from 1 to infinity, there's an infinite bound up here. That is considered to be improper. Okay? As well as an integral with a discontinuity on the interval a to b. So thus far, when you went through Calculus 1, all of the integrals that you wrote or that you worked with, there were no improper integrals. None of them had a discontinuity between the two bounds that you were working with. So the idea here would be if I gave you an integral from 1 to 5 of 1 over x minus 4, well, you would say, well, x can't be 4, and 4 is between 1 and 5. That's a big problem, okay? Well, it's not an impossible problem to work with, but it is a problem. It makes the integral improper, all right? So today we're going to learn how to evaluate improper integrals, okay? All right, so let's start with the first example. I want you to integrate for me from 1 to infinity 1 over x squared dx. So the first thing you need to do is understand the notation. So the problem is we can't take infinity and substitute it in, so to speak, all right? Although in our head, I'm sure a lot of times we do that, okay, especially when we're calculating limits, but mathematically it's not allowed. So we need to get rid of this infinite bound up here. To do that, instead of saying we're going to integrate from 1 to infinity, we're going to say we're going to calculate the limit as b approaches infinity of the integral from 1 to b of 1 over x squared, which we're going to switch around and make x to the negative 2 with respect to x. All right? So we're going to need to write this notation. This notation has to be written correctly. Your integral has to be written like that for you to be able to evaluate it. All right, so the limit as b goes to infinity, we can integrate x to the negative 2 pretty easy. It's a straight line from 1 to b. Add 1 to the power, divide by what we get. We get x to the negative 1 over negative 1, which we can, clean up here a little bit. And write from 1 to b, negative 1 over x. And now I'm going to substitute the numbers in. I'm still trying to find the limit as b goes to infinity. So that's negative 1 over b minus negative 1 over 1. All right, now we're going to try to find the limit. The limit as b goes to infinity. As b goes to infinity, 1 over something really big is really small. It goes to 0. Two negatives make it positive. 1 over 1 is 1. My answer is 1. So the value of this limit is 1. Okay? Now, there are two additional words that we can talk about here. Okay? If the limit or if the improper integral approaches a finite value, we say that this integral is convergent. Converges. Converges. Convergent. Okay? Improper integral approaches a finite value. If the improper integral does not approach a finite value, it ends up going to infinity or something, or negative infinity, we would say that integral diverges or is divergent. All right, so the improper integral does not approach finite value. Okay, so since this integral approached 1, So the value of this integral is 1. It also means the area that's underneath the curve, 1 over x squared, from 1 all the way to infinity will be 1. And we would say this integral converges. Okay, or is convergent. All right? So these are some of the things you need to be able to look at. Okay, let's try the same thing. We'll try the integral from 1 to infinity, 1 over square root x dx. Same idea. So again, we're going to swap out this infinity symbol for a limit. So we're going to take the limit as b goes to infinity, the integral from 1 to b, and then 1 over square root x, we're going to make x to the negative 1/2. We're going to add 1 to the power, divide by what we get. So that's going to be the limit as b goes to infinity, straight line from 1 to b, x to 1/2, right? Add 1 to the power, divide by what you get, divide by 1/2, which means you're multiplying by 2. All right, so that's going to be the limit then. We'll substitute in, use our fundamental theorem. It's going to be 2b to the half minus 2 times 1 to the half. So 2b to the half as b goes to infinity. So the square root of infinity, so to speak. Now square root x looks like that, right? So it goes real slow, but it does eventually get to infinity. So this is infinite, this term is infinite, and then this is 2. So the value of this is infinity, right? So the value is infinite. So we say this integral diverges or is divergent. Okay? All right. All right, let's try again. From 1 to 3, dx over x minus 1. Okay, so this one's a little bit different. There's no infinite bound in here, but one of the actual bounds themselves, the function's discontinuous at this bound, right? If I plug 1 in, I get 0 in the denominator. That's no good. So I'm going to rewrite this in a different way. I'm going to take this bound out of here. This bound is causing me issues, right? I can't substitute 1 in. So instead, what I'm going to do is find the limit as a approaches 1, and we'll fill in the rest in a minute here. From a to 3 of dx over x minus 1. Okay? Now, as a approaches 1, well, remember, we want to be careful about, we don't want a to approach 1 from both directions, right? Because we want to keep the area that you're finding, so to speak, between 1 and 3. So we actually want to approach 1 from this direction so that we keep the value between 1 and 3. So we're going to say as a approaches 1 from the right. Okay? And again, that all needs to be part of your representation here to integrate this. All right, so we're going to keep the limit as a goes to 1 from the right. We can use substitution on this. U would have to be x minus 1. Du would be dx. It would be a straight substitution. So we would end up with du over u, right? We'd end up with du over u. And then, look, we could just integrate this thing. It's going to be the natural log of the absolute value of u, but u is x minus 1. Hopefully we can go ahead that far. And this is going to be straight line from a to 3. So now we're going to substitute in. So the limit as a goes to 1 from the right, the natural log of the absolute value of a minus 1, minus natural log of the absolute value of 3 minus 1. So as a goes to 1 from the right, you get 1 from the right minus 1. That's the natural log of 0. The graph of the natural log, there's a vertical asymptote here. And that's the graph of the natural log. As the natural log goes towards 0, as this function goes to 0 on the y, it goes down, or x, then y goes to negative, this is negative infinity, minus ln 2. So you can forget it. This is divergent here, because we end up with one of the evaluations being at infinity. All right? So again, what would it mean? It would mean the area that's underneath this curve would be something like negative infinity, so to speak, if you could calculate it. All right? But again, we don't calculate that. Okay, let's try one more. We're going to integrate from negative infinity to 0 x over, or x times e to the x. So let's take this negative infinity out of here. We got the limit as a goes to negative infinity. Then the integral from a to 0, x e to the x dx. So now the question is, how do I integrate this thing? Well, x times e, these are multiplied. I can't use substitution. This is a parts problem. So I'm going to try to lip it here. I need a u and I need a dv. So my u is going to be x. It's a polynomial. dv is e to the x dx. So du will be dx. V, I'm going to have to integrate both of these, will be e to the x. So let's see. Parts is going to be, a goes to negative infinity. uv, that's straight line from a to 0, x e to the x, minus the integral, a to 0, v du. All right, so I can integrate that one. So a goes to negative infinity, straight line from a to 0. We'll evaluate in a minute. Minus, this is straight line from a to 0. Oh, oops, x e to the x, forgot it. Integral of e to the x is itself. All right, so now we got to evaluate this thing. So this is the limit as a goes to negative infinity. Let's substitute it in. We got 0 times e to the 0 minus a times e to the a minus e to the 0 minus e to the a. Okay. So a goes to negative infinity. Let's see. Let's sort out some of these other terms first. Let's do it in another color, make it a little bit easier to see and recognize. 0 times e to the 0, that's going to be 0. Whoa, that's not what I was going for. That's a highlighter. So that's 0 there. A times e to the a, we'll do that in a minute. E to the 0, that's 1. E to the a, as a goes to negative infinity, so e to the negative infinity, that's really 1 over e to the infinity. So 1 over something really big is really small. That goes to 0. So now the only question is a e to the a. So let's do that over here. I want to find the limit as a goes to negative infinity of a e to the a. So if I were to substitute that in, that would be negative infinity times e to the negative infinity. So e to the negative infinity, if I put that back on the bottom, that would be negative infinity over infinity, right? So let's write it here. So that way maybe it's a little bit easier to see. We don't normally do this. We don't substitute infinities in. It doesn't make sense, but I think it's easier to see it here. If you write negative infinity times e to the negative infinity, that's going to be negative infinity over e to the infinity. So that's negative infinity. E to the infinity is infinity. Negative infinity over infinity, that's indeterminate. Okay? That's indeterminate. So now you can use L'Hopital's rule to do this. So this is the limit as a goes to negative infinity. Let's rewrite this with a numerator and a denominator. And we're going to use L'Hopital's rule. So derivative of a is 1. Derivative of e to the negative a is e to the negative a times negative 1 with the chain rule. So now as a goes to negative infinity, 1 over e to the negative a, so that's e to the negative infinity. Right? Let's write it again. I think that's easier. So that's e to the infinity times negative 1. So 1 over something really big is really small. That goes to 0. So this is 0 also. And all told, after we do all this math, the result we get is negative 1. So this converges to negative 1. This integral, if I were to evaluate it, converges to negative 1. Okay, and there might be one more problem. Let me see. Yes, one more. And then we'll call it a day here on this one. So we're going to try from 0 to 9, dx over the cube root of x minus 1. So again, now we have another issue here. So this is our final issue. I can't substitute 1 into this because 1 makes this function undefined, right? It would give me 0 in the denominator. Now, 1 is not a bound. 1 is literally in the middle of the bounds. So I have 0, I have 9, and here's 1. So I'm going to have to split this thing into two separate integrals. So I'm going to have to integrate this thing from 0 to 1. Well, all right, let's do it that way first, and then we'll throw the limit sign in there so that you kind of see where it all shows up, although you probably will be able to see it anyway. We're going to go from 0 to 1, dx over the third root of x minus 1. And then we're going to go from 1 to 9. So we're splitting it up. But now we need limit signs because we can't put 1 there because that's no good. It doesn't go in the denominator. So we're going to need some limit signs. So we're going to need the limit then as b goes to 1 from 0 to b. Let's bring it up, I think. Save ourselves a step. It's going to be x minus 1 to the negative 1/3 dx. And between 0 and 1, you want to approach that way so that you keep your value between 0 and 1. So 1 from the left. And then you're going to have another limit as a goes to 1 from a to 9. Again, it's the same integral that we have to calculate, so that's easy. And then I want to approach 1 from the right to keep myself between 1 and 9. All right, and then to do this integral, I'd need substitution. Let u be x minus 1. To use dx, it's a straight substitution. It would give me u to the negative 1/3 if I look at it over here. So I'm going to add 1, divide by what I get. That's u to the 2/3. So this is going to be the limit as b goes to 1 from the left, straight line from 0 to b. It's going to be u, or x minus 1, to the 2/3 times 3/2. And then the other limit, or the other integral, a1 for the right, is going to be straight line from a to 9, 3x minus 1 to the 2/3 over 2. Okay, and now I'm going to substitute in and see what I get. All right, here we go. So this is going to be the limit as b goes to 1 from the left, 3 b minus 1 to the 2/3 over 2 minus 3 times 0 minus 1 to the 2/3 over 2. That's the first limit. The second limit is a goes to 1 from the right of 3 times 9 minus 1 to the 2/3 over 2 minus 3 times a minus 1 to the 2/3 over 2. Okay, so now let's try to evaluate this. We'll do it in a different color. Maybe it'll make our lives easier here. As b goes to 1, 1 minus 1 is 0. So this term is really 0. This whole term washes out here. That's really nothing. Negative 1 to the 2/3. If I calculate it, negative 1 to the 2/3. That's like squaring negative 1 and doing the 1/3 power of it. So that's 1 to the 1/3, which is 1. So this is going to be 3 times 1, that's a 1, over 2. So that's negative 3 over 2. All right, so from this first integral, we get a contribution of negative 3/2. Then over here, we have 8 to the 2/3. 8 to the 2/3. That's 8 to the 1/3 squared. I think it's easier that way. So that's 2 squared, that's 4. So this whole thing here is a 4. 4 times 3 is 12. 12 divided by 2 is 6. That's a 6. And then if I put 1 in here, 1 minus 1 is 0. That's a 0. This whole thing washes out at 0. So I get negative 3 over 2 plus 6, which is 9 over 2, right? 12 minus 3, 9 over 2. So this converges to the value of 9 over 2. It means the area that's underneath this curve is 9/2 between 0 and 9. Okay? And that's it. All right? As always, thanks for clicking.